to be sure that we are all on the same page, what we know about the spreading centers and the main differences that we have between the fast and the slow spreading ridges. So we will have basically two configurations. At fast spreading centers, the magmatic processes are sufficient enough to accommodate the full divergence, lithospheric divergence, and so this will form a thick and continuous mafic crust made of gabbros and sheeted dikes and volcanics on top, while at slow spreading ridges, the magmatic budgets are locally insufficient to fully accommodate the lithospheric divergence. And so you have some tectonic processes that take into relay the lithospheric divergence, and this results in the exhumation of the deep lithospheric rocks, so basically mantle rocks and gabbroic intrusive. And the most beautiful expression of these tectonic processes is the formation of mantle domes that are well imaged through bathymetry. And these domes are also known as oceanic core complexes, and you can see these beautiful lineations that correspond to corrugation. And actually, these mantle-dominated domains are far to be anecdotic at the seafloor, because they might make up between 10 and 25% of the Earth seafloor, and regionally up to 50%. And obviously, in these environments, where you have mantle rocks that are exhumed at the seafloor, you have some fluid rock interaction that are very particular. And let's say that we have two end members depending on the nature of the deep fluid rock interaction. In one hand, we will have low temperature fluids that vent at the seafloor that are really reduced, that are alkaline, rich in calcium, and these fluids may form the so-called brucite carbonate chimneys that have been observed at the Lost City hydrothermal field. And in the other end, when you have seawater that percolates through the rocks and gets heated at depth, thanks to the cooling of magmatic intrusion, these fluids may be very hot, acidic, reduced, and rich in metals. And when they will vent eventually at the seafloor, they will form this beautiful black smoker and the mineralized system that we know, such as the rainbow hydrothermal field. So this part of the hydrothermalism actually is the emerged part of the iceberg, but something exists when the fluid can react with the rock that are progressively exhumed at depth, and this is the cryptic part. So this fluid rock interaction at depth lead to a variability of fluid rock interaction and of hydrothermal alteration in both gabbroic and rocks, and peridotites. And these fluid rock interaction occurs at variable metamorphic conditions, from very high temperature associated with amphibolite facies condition to low metamorphic condition to green schist or sub-green schist. And for instance, in gabbroic rocks, this is well reflected by the formation of different mineralogical assemblages, such as amphibole, chlorite at high temperature, and prehnite, secondary plagioclase, zeolite even at low temperature. While in peridotites, these fluid rock interaction will mostly lead to the serpentinization of the peridotite, and forming different serpentinization events depending on the fluid rock interaction and depending on the thermal regimes during the fluid rock interaction. And so this hydrothermal alteration lead to the formation of different fluids. In one end, we will have some acidic sulfur-rich fluids during fluid gabbroic rock interaction, while you would produce some very reduced condition during the serpentinization, and so fluids that are enriched in dihydrogen and methane. So we have two different end members. In one end, what we can observe are active hydroformalism at the seafloor, and for instance, regarding the high temperature mineralized system. And in the other end, we also observe some hydroformal alteration and deep magmato-hydrothermal processes that occur during mantle exhumation. But the question is, what could be the link between these deep-seated magmato-hydrothermal processes and the expression of the active hydroformalism at the seafloor? Do these deep-seated magmato-hydrothermal processes can be related to metal mobilities that can further explain the black smoker mineralized fluids that we observed at the seafloor? And this is this question that I would like today to address through this presentation, to better constrain what could be the metal cycling in the oceanic lithosphere mantles, in terms of metal sources, in terms of mechanism of leaching and transport. And I will leave the part about precipitation for today. And so to address this question, I've been working on the Mark area where mantle rocks have been drilled 30 years ago. And this is what we are going to see. So here we are in the Mark area, which correspond to the southern intersection between the Cane fracture zone and the actual Rift Valley at the Mid-Atlantic Ridge. And basically, this western area corresponds to an oceanic core complex, which has been drilled. And there, they mostly recovered serpentinite asbogite, cross-cut by different magmatic veins and dikes. And so during this study, we focused on serpentinite peridotite and their equivalent that have been that are cross-cut surveyed by different types of veins. Magmatic veins that are now partially to completely altered. So this is the picture that are highlighted here by this orange square, where you can still see in some instances the former igneous mineral such as clinopyroxene, while in other instances the primary mineralogy is completely replaced into secondary phases. And we also focus on serpentinite peridotite cut by hydrothermal veins. And this variability of texture is supposed to be representative of the magmato-hydrothermal processes that occurred in mantle rocks during their exhumation. So zooming on these veins, we performed a petrographic investigation. And so I present you here some picture of the mineralogy present in the veins. In the magmatic veins are partially completely replaced into secondary minerals, mostly amphibole, secondary clinopyroxene, chlorite, talc, serpentine, also that suggest hydrothermal alteration that took place at variable thermal regimes, from amphibolite to lower green schist type facies condition. One interesting observation was to see that at the contact between some magmatic veins and the host peridotite, iron and calcium-rich metasomatism occur. And this was responsible to the formation of different phases, namely ilvaite, which is iron and calcium-rich ferrosilicate, but also hydrogarnet, amphibole, and clinopyroxene. And some of these silicates directly replace the mantle olivine, which is at the contact with the magmatic veins. And this olivine is not recrystallized, which means that this iron and calcium-rich metasomatism occurred prior to or during early serpentinization of olivine, which constrained the temperature formation above 350 degrees C, which is the stability field for olivine. And also some of these iron and calcium-rich silicates are also found in hydrothermal veins that cut through the serpentinite peridotite, and where you can find clinopyroxene, hydrogarnet associated with calcite and serpentine. And here we also observed some mineralization and pyrrhotite, which means that during the fluid circulation and this hydrothermal veining, the fluid was rich in sulfur and transported metals. So to better understand the behaviors of metals during these different magmatic and hydrothermal processes, we performed geochemical tracing. And I present you some metal of interest through these different diagrams. So for iron, copper, and zinc. And so the symbols here are the orange dots correspond to the serpentinized peridotite cut by former magmatic veins. The pale green dots correspond to the serpentinized peridotite cut by hydrothermal veins. And the green dots correspond to serpentinized peridotite. We observed for iron that the serpentinized peridotite cut by former magmatic veins are quite enriched in iron and have lower magnesium number, magnesium which is represented by these gray dotted lines, compared to the typical serpentinized peridotite of the mark area. In terms of trace element metals, so copper and zinc, we plotted them against a proxy for free drug interaction, which is the rubidium-niobium ratio. Why this ratio? Because rubidium is a fluid mobile element, while niobium is relatively immobile in fluids and is quite enriched in melts. So during free drug interaction, you would expect to increase this rubidium-niobium ratio in the hydrothermal rocks. And so if we look at the copper first, we observe that the copper content of the serpentinized peridotite cut by former magmatic vein is quite low. And it's even quite low if we consider a mixing between a peridotite and which is represented here by this gray field, and a magmatic vein that correspond to this gray diamond. So this means that copper has been leached during hydrothermal alteration of the magmatic veins. But this hydrothermal alteration had probably negligible effects on the zinc mobilization. Another interesting observation here is that the serpentinized peridotite cut by hydrothermal veins present the highest rubidium-niobium ratio and are enriched in metals, in copper and zinc, meaning that the fluid from which the vein formed was enriched in metals. And so we have different behaviors of the metals regarding of the magmatic or hydrothermal processes. So we wanted to dig a bit more about the processes that control these behaviors. And so if we start with the ion enrichment, it can be either due to the melt addition itself in mantle peridotite, but as the magmatic veins are partially to completely altered, it's quite a challenge to retrieve the original composition of the magmatic veins. But this can also be due to interaction between the melt and the host rock. And so to test this, we performed some geochemical analysis on the mantle silicates, so olivine, which is a major silicate in our mantle rocks. And so we observed that olivine at the contact with the magmatic veins represented in orange are quite enriched in iron and depleted in nickel compared to the olivine, which are far away from these magmatic veins and which are represented here in green. So this was not really a big deal. I mean, so 30 years ago, it has been already seen that this such modification of the chemical composition of olivine could be triggered through melt rock interaction. But what was interesting was also to observe that these olivine are also not only enriched in iron, but also in some other metals such as cobalt and zinc. And through this melt rock interaction, we can produce very important enrichment in this metal in the mantle silicates. If we look now at the mechanism responsible for copper leaching in the mantle rocks cut by former magmatic veins, we looked first at the hydrothermal condition during this leaching, and so we performed some geochemical measurement on newly formed phases during hydrothermal alteration. So a very good target is amphibole, because amphibole is ubiquitous in these magmatic veins. And so we have several lines of evidence that point to water-rock interactions that occurred at variable thermal regimes. First, the mineralogy of amphibole range from pargasite, which is high temperature magmatic amphibole, towards tremolite, actinolite, the low temperature amphibole stable in green schist fascist condition. We applied also a titanium thermometer to this amphibole, and it yields a temperature range in between 420 degrees C to 830 degrees C, which is quite in good agreement with the mineralogy, which is in between the subsolidus conditions and the green schist and upper green schist fascist condition. And finally, looking at the rare earth element composition of the amphibole, they present, even in the same vein, they present a great variability of their composition. And we have the early amphibole that directly replace the clinopyroxene, the igneous clinopyroxene, that present the highest rare earth element composition with a typical negative europium anomaly. And during progressive amphibole recrystallization at variable thermal regimes, we observe a decrease of the rare earth element composition of our amphibole, and this is accompanied with the apparition of a positive europium anomaly that might suggest that plagioclase were able to react with the fluid during the amphibole crystallization. So to better understand now the mechanism of copper leaching and the complexes that transported the copper, we performed some isotopic tracing. And so I present you here a Rayleigh distillation model, so this graph is the copper isotopic composition versus the copper content of the different samples. So to make it a bit simple, so what we try to do is to model the isotopic fractionation during interaction between a fluid that leach out the metals from different copper-bearing phases. So for instance, chalcopyrite, cuprite, or copper-bearing silicate. And we model this at different temperature to understand the hydrothermal condition during the copper leaching. And what we observed is that if we consider fluid-rock interaction at low temperature, so 300 degrees C, we cannot reproduce the geochemical composition of our samples. While if we consider fluid-rock interaction at higher temperature, 600 degrees C, and if we consider that the copper derived from both chalcopyrite and cuprite, so from both copper sulfides and copper oxides, we can nearly reproduce the geochemical composition of our serpentinized peridotite cut by magmatic veins. So this means that copper leaching probably occurred at high temperature, and this temperature is in good agreement with what we found from the titanium thermometry in amphibole. And finally, the last element of metal mobility that we observed was this metal addition in the hydrothermal veins. And so hydrothermal veins, they cut through the serpentinized peridotite, suggesting that they formed during or after the serpentinization, so that restricts the temperature range below 400 degrees C, which is the temperature below which serpentinization is kinetically efficient in mantle rocks. And so once again here, we try to understand the condition of metal addition and in the hydrothermal veins using a geochemical modeling survey. So here the approach was a bit different. We tried to model the interaction between serpentinized peridotite and the fluid, which would have already interacted with different metal-bearing phases to leach the metal. So as far as you move towards the right, you add more and more metal in your system, and we modeled this at different temperatures from different sources of metal, and we observed that our geochemical composition of our serpentinized peridotite cut by hydrothermal veins can be explained by fluid rock interaction at 300 degrees C from a fluid which would have leached out the copper from chalcopyrite and which would have leached out the zinc from spinel, while if we imagine another source of zinc, for instance sphalerite, we cannot reproduce the isotopic composition of our samples. And if we imagine lower temperature during fluid rock interaction, we cannot neither reproduce the isotopic composition of our samples. So if we try to put everything now in let's say in a model, in a magmato-hydrothermal model, we have seen different steps corresponding to the magmato-hydrothermal evolution of the rock at the mark area. Starting with early melt rock interaction during the percolation of magmatic veins through mantle rocks, and this stage, during this stage, we had some enrichment in metals, iron, cobalt, and zinc in the surrounding mantle rocks. On top of that, during high temperature fluid rock interaction, we stabilize iron and calcium-rich silicates in the surrounding mantle rocks, while the magmatic veins get progressively altered and the copper was progressively leached out from the magmatic veins. And then during progressive mantle unroofing and exhumation at the seafloor, probably that seawater circulation progressively led to the pervasive serpentinization of the residual peridotite. And during this stage, both fluid magmatic rock and fluid mantle rocks interaction led to the formation of hydrothermal veins rich in sulfur and in metals in the serpentinized peridotite. So if we try now to dezoom a bit more and to think about where this deep-seated hydrothermal process and iron calcium metasomatism might occur in present-day system, we have actually two different configurations where I think it could occur. First, during mantle exhumation along a detachment fault, so below the serpentinization front, so at higher temperature, if we have some magmatic inception in a fresh or poorly altered mantle peridotite, we could trigger this the same magmato-hydrothermal processes. And another setting would be after mantle exhumation at the seafloor, if we have some late normal faulting that affect the massif. This area could be also a good setting where iron and calcium metasomatism might occur. And actually, this second setting corresponds to the Rainbow Massif. And at the Rainbow Massif, some seismic studies have evidenced the presence of reflectors, and these reflectors have been interpreted as molten magmatic lenses that incept in the deep basement below the rainbow hydrothermal fields. So it is likely that these magmatic lenses incept in a non-serpentinized or poorly serpentinized mantle, and so we might have the similar melt-rock interaction that occur in this setting. And if we consider that some fluid can react with these deep zones to react with the metasomatized mantle rocks, we should be able to find the signature of these deep-seated magmato-hydrothermal processes in the chemical composition of the fluid venting at the rainbow field. And indeed, if we look at the composition, the metal composition of the fluids at rainbow, it is quite enriched in iron, in zinc, and in cobalt compared to the other black smoker-like fluids that vent at the seafloor in different mineralized systems. So here we can probably point to genetic links in between the deep-seated magmato-hydrothermal processes and the fluids that vent at the seafloor and that form mineralized systems. And to conclude about what we have seen quickly, I hope that you are convinced that the oceanic lithospheric mantle has the viability of deep-seated melt-rock and fluid rock interactions, and that these processes exert a strong control of metal mobility. Early melt-rock interaction can be a suitable process to enrich the surrounding mantle rocks in iron, in cobalt, and zinc. And further fluid rock interaction can exert a strong control either on copper mobility during high temperature fluid rock interaction, and can also provide some metals to the serpentinized peridotite and form mineralized veins. And I thank you very much for your attention, and I'm happy to take some questions.
Well, thanks a lot for the invitation. I'm really happy to join the serpentinite community. And I would like to present some of the work we've been doing on ultramafic-hosted VMS deposits and why we think this type of deposits have been overlooked and they should be considered as a standalone subclass of VMS deposit. So, as you might be very well aware, hydrothermal circulation in the oceanic crust is very important for buffering both the oceanic crust and the ocean composition, but it's also very important for the formation of VMS deposit, which is kind of the uppermost expression of this large-scale hydrothermal fluid circulation within the oceanic crust. So when the hydrothermal fluids vent on the seafloor, you have the formation of VMS deposit. And we know that VMS deposits form in many different tectonic environments associated with the oceanic crust. We know they form in fast-spreading ridge, in slow-spreading ridges, but also in super-subduction zone environments, such as in fore-arc environment, island arc, and back-arc environment. And because they form in such diverse environment, they actually have different type of metal endowments, which is actually controlled by their host rock. And so this has led to the classical classification of VMS deposit based on their host rock. That was done by Barry and Hamilton, which is a very classical paper for VMS deposit. And there are 5 groups for VMS deposit. There are the mafic, bimodal mafic, mafic siliciclastic, bimodal felsic, and bimodal siliciclastic. And because they are hosted in different rocks, they have different metal endowments due to the metal concentration in these rocks. So for instance, you can see that mafic hosted VMS deposit, they tend to have higher copper concentration, while the siliciclastic or the felsic ones tend to have higher zinc and lead concentration. So this is all very normal for VMS deposits. And the question that we have today here is that maybe we should consider another subgroup, which is the ultramafic ones, and why we should be interested in those ones. So ultramafic-hosted VMS deposits are not new by any means. They've been known for a very long time in the community, but they have been often referred to specific localities. So there's been the Outokumpu type from Finland, the mineral fault type from Russia, but the most recent or the most common classification is the ultramafic-hosted VMS deposit, or seafloor massive sulfide deposit from the review by Fouquet et al. In 2010, which focused on the mid-Atlantic ridge seafloor massive sulfide deposits. So where do we find them? So you know that the oceanic crust is a, let's say, realm of amazement where there's very diverse magmatism, deformation, and circulation and everything. And if you just compare a fast spreading ridge environment, such as the East Pacific Rise, with a slow spreading ridge environment, such as the Mid-Atlantic Ridge with the cane that Rémi just talked about, we have very different structure and oceanic crust. And as Rémi very well introduced, in slow spreading ridge environment, we have the formation of oceanic core complexes. And oceanic core complexes are very important. I will not talk too much about that, but the main thing is that they allow to bring to the surface the deep seated rocks, which are gabbroic and ultramafics, which end up onto the seafloor, and you have extensive hydrothermal fluid circulation associated with this exhumation process along the low-angle detachment faults. And eventually, that's very efficient for mobilizing the metals from the hydrothermal alteration zone to the venting site where we have the formation of the VMS deposits. And this is how you can form this ultramafic hosted VMS deposit. So here we have a simplified genetic model for the formation of this ultramafic hosted VMS deposit. So we have the low-angle detachment fault. We have a bit of gabbroic intrusions in the system that provides heat to the system. Also some kind of high temperature metasomatism that Rémi just talked about. And during a fluid rock interaction, you're going to leach out the metals, most likely from the lower part of the crust. Then the high temperature buoyant hydrothermal fluids will rise towards the sea floor, where they eventually vent into the foot wall, forming the ultramafic hosted VMS deposits, or into the hanging wall, but these will be more mafic type deposits. And they can also be subsea mineralized system. So the main thing is these are hosted in ultramafic rocks. They are associated with the low detachment faults, and enrichment are mostly copper, zinc, cobalt, nickel, and gold, which we'll look a bit more about that. So we see a lot of seafloor massive sulfide, ultramafic hosted seafloor massive sulfide deposits in Mid-Oceanic Ridge from the seafloor expedition. A lot of them have been discovered along the Mid-Atlantic Ridge in the 2000s. And more recently, from the exploration of the Indian Ocean, there have been more and more discovery about such type of deposits. And so it seems like the more we look at slow spreading ridges, the more ubiquitous they are. And so they are really common type of mineralization in slow spreading ridge environments. They also have been discovered in the Arctic Ocean. And so the question that we have is that we see them on the seafloor very much, but they appear to be quite scarce in the geological record. And that's one of the questions that we had. Like, they are assumed to be scarce in the geological records, and we were wondering, are they really scarce in the geological record? And should we be looking a bit more in detail for them? Because some of the problem with this type of deposit is that they are hosted in ultramafic rocks, often highly deformed serpentinized, and they can be very easily overlooked or misinterpreted, such as for magmatic nickel copper PG type mineralization. So what we wanted to do is to look carefully at different type of mineralization and try to classify them as ultramafic hosted VMS deposit or not. So here you can see on the all these are the mineralization we've been focused on, and to see if they can be classified as ultramafic hosted VMS deposits. So yeah, so if you go in the field and you find a sulfide mineralization, and if you want to know if this sulfide mineralization is ultramafic hosted VMS deposit, you can look at 4 criteria, which are those ones, which is the host rock and alteration, the structural control, the ore texture and mineralogy, and the metal endowment of the deposit. So the host rock, so the protolith of the host rock are mainly Innsbruck and donite, but they are extensively serpentinized and deformed, and they're also often associated with gabbros and dikes. And the alteration, so in addition to serpentinization, you often have different type of magnesium, calcium, silicon, iron, and carbon metasomatism. So everything that you can find on the seafloor, such as ophicalcite, talc, or magnetite, or high temperature metasomatism, such as ilvite and stuff that Rémi just presented beforehand. And obviously, everything is very strongly deformed. So what you can see on the top right corner, this is a detachment zone into the trudosulfonite with different type of metasomatism. So the bottom right corner, this is pure magnetite. So the serpentinite has been fully replaced to pure magnetite. In the middle, this is ophicalcite, and the bottom left, this is talc alteration related to these detachments, which are very close to sulfide mineralization. Also the structural control. So the deposits are often very closely related to the detachments or to high-angle faults that form within the detachments. So you can see on the top right corner, you have the Dorganish deposit in the main ural fault, where you have ultramafic rocks in green and highly serpentinized rocks in pale green, and the sulfide mineralization is within this highly deformed and serpentinized rock, which is just at the contact, which is the blue line, and the green line, the red line, sorry, and which is the detachment. But it can also be in the high angle faults. That's the case for the Repia deposit in the Illugarite in Italy, where it's developing late during the evolution of the detachment. So there is always a very strong structural control of mineralization. Then about the ore itself. So the texture of the ore, you often have similar things to classic VMS deposits. So you can have massive sulfide or stockwork type, also veins. But on top of that, they can be quite banded, deformed, tabular, or also brecciated or clastic. And the ores, the mineralogy is mainly pyrrhotite, chalcopyrite, carbonite, with a bit of sphalerite and pyrite. And that's one of the main reasons why this type of deposit is often misinterpreted as magmatic sulfides. It's because it's the same type of mineralogy sometimes, often. But you also have common cobalt and nickel bearing minerals, such as sulfur arsenites and arsenites, which are quite common in cities. About the ore grades, so they mostly classify as a copper-rich deposit, which is very similar to the mafic-hosted VMS deposits. The copper grades are usually over 1% weight percent, where zinc is a bit lower, and the nickel and cobalt enrichment is quite variable. You have a high copper to nickel ratio, and you often have some gold enrichment as well. It's not systematic. They're not really gold rich, but they have a bit of gold enrichment. And that you can see in the bottom right ternary diagram. And also what's important is that they are really PG poor and lead poor. So this is very useful, especially for the PG, to make the difference with the magmatic sulfide deposits. So once we have gone through all these criteria, we use a kind of matrix classification where we fill up all these boxes based on the field observation for each deposit, and we establish a kind of a criteria to allow this classification and to make the difference between different types of mineralization. So either if it's a ultramafic-hosted VMS, magmatic sulfides, or more mafic-hosted VMS. And depending on the score of this matrix, based on the different criteria, that give us confidence in our classification for the VMS deposit. So when we did this work, we realized that a lot of these deposits were actually in different type of ophiolites. For instance, Rémi has been working a lot on the Plata, which is an OCT environment, while we have been working in Cyprus, where we also have this type of mineralization, which is a super-subduction zone environment. And so we're a bit curious about where we find this deposit in the geological record. So we need to look a bit more in details in the type of ophiolites in which these deposits are present. So we're going to look to focus on three types of ophiolites. So the subduction unrelated one, so the continental margin type of ophiolites, or OCT, the mid-oceanic ridge type of ophiolite, and the suprasubduction zone type of ophiolite on the top right corner. So these are the three types of ophiolites we have been focused where we have been focusing our work. So to classify the ophiolite in which the deposit form, we also use different criteria. The first one will be just first order geological consideration. How does the ophiolite look like? Do we have a really nice Penrose type ophiolite, such as in Cyprus, which will be more or suprasubduction zone environment? Do we have this kind of discontinuous or dismember ophiolite, which is very common for OCT environment? Or do we have a special proximity to volcanic arc, which is more common for suprasubduction zone environment, such as the main Ural fault? Another criteria is to look at the stratigraphic consideration of the nature of the sediments that develop on top of the detachments. So if we have more pelagic dominated sediments on top of the detachment, this will mean it's more higher depth, so we may be more mob environments. Or if we have more detrital dominated sediments on top of the detachment, this will be more closer to the continental margin, so that might be more OCT So that would be another criteria to help to understand the environment of the ocean, of the ophiolite. The third one, and maybe the most important one, is to look at the geochemistry of both volcanic rocks, which are present within the detachments hosting the mineralization, and also at spinels, which are also present within the ultramafic rocks. So on the left diagram, you have titanium versus vanadium for volcanic rocks associated with the detachment hosting the mineralization, and you can see, well, first a lot of points, it's a bit messy, but you can see all the red dots, they're plotting more or less into the island arc tololites, or bodonites, while the OCT in blue plots more in the marble environment. So we can see already we have different type of ophiolite setting here. Then the green ones are a bit more scattered and maybe mixed environment. On the right corner, this is also for chromite composition, depending on the titanium and aluminum content. You can see on the right part you have the marble environment, while into the left part you have the more suprasubduction zone type environment. And we can see, depending on the locality, we have different geochemical signature. So that's also another tool that helps us to characterize the ophiolite where the mineralization are present. So to characterize the ophiolite, we do a similar approach as for the mineralization. We make this kind of matrix where we use every criteria and we characterize if it's marb type, an OCT type, or suprasubduction type. And that at the end, it gives us confidence in the classification of the ophiolite with what we're dealing with. And so ultimately what we end up with is that this type of deposit are actually forming in three main type of environment. The mid-oceanic rich one, as we can see from the seafloor, but it's not limited to this type of environment. We also see them in ocean continent transition environment and also in suprasubduction zone environment. And so why is that important? Well, first, because ocean continent transition and suprasubduction zone environment are better preserved in geological environment. It's much easier to abduct this type of crust in a mid-oceanic ridge. And so we have better chance to preserve the ultramafic VMS deposit due to the geological record. There are also implications for seafloor exploration. It has been focused mainly on mid-oceanic ridges, and perhaps it's worth to look at other type of environment, such as in OCT or suprasubduction zone environment, where we might find this type of high temperature geothermal vents associated with sulfides. And also to finish, there are also, we think, some potential for new discovery for this type of VMS deposit. So if you look to the left diagram, you can see the tonnage of the different ultramafic-hosted VMS deposits, and they have been ranked based on their size. And then the black line is a zip flow, which is a predictive distribution for any given type of deposits. And the assumption, if you look at our deposits in general in a district or an area, you have the biggest deposit with a given tonnage, and the next deposit will have half that tonnage, and the next one will be half the tonnage, and so on. So it follows this kind of distribution curve. And so when we plot the deposit we know about on top of this predictive distribution curve, we actually see there's a lot of cap in the distribution. And these caps suggest that maybe there are some deposits that are left to be discovered. And this can be put in parallel with the diagram to the right, which shows the overall decrease in VMS discovery since the 60s. So we have the time and the tonnage, the discovery of VMS in tonnage. And we see that since the 60s, with the development of geochemical exploration, we have less and less VMS discovery. And so that kind of shows the general trend where we have less and less ore resources, while we need more and more for the energetic transition. So this could be an interesting type of ore deposit to investigate in the future. But they need specific exploration methods which have not been developed yet.